So today we're going to be talking about the Model 441 and 461 gas regulators. Last time we had a webinar on how to size regulators, and in the future we're going to have webinars on the 243 commercial regulator. We might do a webinar on the service regulators, and then we'll run back the 441, 461 presentation and the sizing presentation again this year for anyone who missed it. But we're going to go ahead and get started on the 441, 461 presentation here. So today we're going to discuss, I'm going to give a brief introduction on USG, and a lot of you guys have heard that before, but if there's anyone new on the call who's not familiar with us, just want to give a quick introduction on USG. And then we'll talk about the components and operation of these regulators. We'll talk about the models and features associated with these regulators. We'll talk specifically about the rollout diaphragm, the maximum inlet pressures and specs on these regulators, and then we'll talk about installation examples, and then some resources that we have, and then how to troubleshoot these regulators. So let's talk about some names you'll see on these regulators in the field. These regulators started as Chaplin-Fulton regulators, a company that started in the 1830s. And they designed the 441 regulator in 1944 and the 461 regulator in 1946. We believe that the 57S rollout diaphragm was invented in 1957, and then they were sold to Rockwell Manufacturing in 1963. I like to pull up this slide whenever I'm talking about our regulators so that you're familiar with the different names that you might see out in the field. If you see a regulator and it is a Chaplin-Fulton regulator, a Rockwell regulator, Equimeter, Invensis, Census, or USG, we're all talking about the same regulator model, just under different brand names throughout the years. And these 441s and 461s go back a long time. So you might see a Rockwell out in the field and it's a 441 57S. Know that that's the same regulator that we're talking about today, and all the data sheets and information still apply. So in 2021, the census regulators were sold to Utility Solutions Group. So in 2021, USG purchased the service regulators, the 143s and 496s. And then in 2023, USG purchased the rest of the commercial and industrial regulators and relief valves. USG has common ownership with the gas distributor in Ohio, and historically has sold these regulators in Ohio, Pennsylvania, West Virginia, Kentucky, and Indiana. And with this acquisition, the manufacturing was moved to Du Bois, Pennsylvania, from Du Bois, Pennsylvania, to Columbus, Ohio. And this acquisition is going to allow Census to focus on making the best regulator. This acquisition is going to allow Census to focus on making the best smart metering products like ultrasonic meters and meter reading systems, while it will allow us to focus on reinvigorating this regulator line, bringing down lead times, coming up with new models, and looking towards the future for regulators. Couple notes here on compliance and future projects. Just note that our quality management system is certified to ISO 9001. And because our regulators are made here in Columbus, Ohio, with primarily American suppliers, they are BABA compliant. So if you have any projects where this comes up, just keep that in mind that we check those boxes. And we'd be happy to provide a letter or documentation if you have any projects that require it. So we offer a number of different regulator models to meet any application, from small regulators for houses and appliances to large industrial regulators. Here you can see we have service regulators, farm taps, relief valves, industrial regulators, commercial. And we'll dive into these models a little bit more here. So we have two service regulator models, the 496 and 143, and those are great for residential and light commercial settings. You'll see these regulators on houses throughout the country. The 046 regulator, the third one down there on your left, that one is a farm tap or first cut regulator. That's great for cutting down a small amount of gas from really high pressures, up to 1,000 pounds inlet on that 046. Then we have the 243. The 243 is our commercial regulator. It's used on a wide variety of applications. The 243 RPC is our only pilot operated regulator, again, used on grain dryers or applications that require like plus or minus 0.5% accuracy. And then the 121, 122 are combustion regulators used on boilers, burners, furnaces, and other gas-fueled equipment. Today, we're going to be discussing the regulators on the right-hand side of the screen, our 441s and 461s. And we'll get into these in these models in more detail here. We also have three relief valves there on the bottom end of the screen, the 257S, the 250S, and the 250DW. And those relief valves are built very similar to our industrial regulators and are great for an additional form of overpressure protection. So when we look at applications for the 441 and 461 regulator, what are these regulators used for? I really see two main applications that utilities are using these for. They're putting them on the regulator stations or purchase points, and then they're using them for their large industrial customers, their big users. We see these regulators used all of the time on regulator stations and large industrial customers for gas utilities. They can be used on industrial gas equipment as well, and we see these regulators installed throughout the entire United States and Canada on really these two main applications. So when we look at components of a regulator, there's a couple key components I wanted to highlight here. First, we have the diaphragm, and that sits right in the middle of the regulator there. You can see on the screen. And that's used to sense downstream pressure, and that pushes up on the spring. So the downstream pressure on this regulator comes in through the control line and pushes up on the diaphragm there. That downstream pressure pushing up on the diaphragm pulls that valve stem up, acting to close the regulator. Meanwhile, the spring on the top of the regulator, that pushes down on our valve stem, providing a force to open the regulator. So the spring's pushing down to open it, and then the downstream pressure is pushing up on the diaphragm to close the regulator. And the balance of those forces, if the downstream pressure is really high, it's going to push up on that spring, closing the regulator. If the downstream pressure drops, the force of the spring is going to overtake that, pushing down on the valve stem, opening the regulator. And the regulator opens and closes by allowing gas to flow through the orifices. This regulator shown on the right has two orifices, a top and a bottom one, and gas can flow through those orifices from the inlet side to the outlet side. The orifices restrict the gas flow, and as that orifice restricts gas flow, that restriction in flow causes a decrease in pressure. And so the whole purpose of the regulator is to drop the gas pressure. Here you can see a picture of a cutout of a regulator. This is a 44157S regulator. And here you can see on the left-hand side, you can see that spring coil pushing down on the diaphragm. The diaphragm's that black component there. Let me see if I can. If you can see my mouse, then the diaphragm sits right here. You have your spring on top pushing down on that diaphragm. And then here's our valve stem. And here you can see this is a top orifice here, and the gas will come through the regulator, up through that top orifice, and then out the right end. On the right-hand side of our screen, we can see the double orifices here. So you can see where the gas can enter into that orifice there and then out the regulator. Here you can see that as well. All right, so when we look at how a regulator operates, here's a little graphic I made. So this is a direct acting regulator. 441s and 461s all operate this way. So here's a regulator that's closed, and you can see here gas cannot. Let me back up. This red here is our high pressure gas, our inlet side, and then the blue is our downstream gas on the low pressure side. So here, gas cannot go through from the inlet to the outlet. The valve seat here is up against the orifice. So the regulator is closed. So if a boiler downstream were to kick on and gas would be drawn into that boiler, the downstream pressure would start to drop. As that downstream pressure starts to drop, the force of the spring overtakes that, pushing down on the valve stem, opening the regulator. So now gas can go through each orifice. building the downstream pressure back up. So now the regulator is open, gas is flowing from the inlet to the outlet, feeding that boiler. Now, if that boiler were to turn off, the downstream pressure would start to build up. That would push up on our diaphragm, closing the regulator there. That pressure, that downstream pressure that it settles at after that boiler turns off is slightly higher than the set point, and we call that the lockup pressure, or sometimes it's referred to lock-off pressure, and that pressure is slightly higher than the set point. So if you can imagine here, when the regulator is open, everything might be running smoothly at 5 psi, and then as that downstream pressure starts to tick up, like 5.1 psi, 5.2 psi, that pushes up on that diaphragm, closing the regulator at a pressure slightly higher than the set point. One other important thing to note on these regulators is that all of our regulators have a vent, and all USG regulators have a vent, whether it's these 441s and 461s or other models. And this vent's extremely important to be able to allow air to flow in and out of that spring tower. As that diaphragm moves up and down, it changes the amount of volume in that spring tower, and we need air to be able to flow in and out so so that diaphragm doesn't get stuck or jammed and can freely move up and down. So if one of the things when we're troubleshooting regulators, we always take a look at that vent and make sure that there is no debris or anything clogging that vent. And if you ever have vent lines, we have requirements on making sure the vent line is clear from debris and sized appropriately so that it can allow air in and out. One other thing to note if you're ever using vent lines, and I really don't see that too often with these regulators, it's usually in our smaller ones, but if you're using vent lines, you never want to share vent lines. You want each regulator to have its own dedicated vent line. All right, so let's get into the 441s and 461s and the different models. So there's 6 models in this family. They can be broken down into 3 groups based on the type of diaphragm case they have and the pressures that they can have. So the first group here is the low pressure regulators, the 441S and 461S. So when I say low pressure regulators here, what I'm really referring to is the outlet pressure that the regulators can be set to. So these 2 regulators here can be set to outlet pressures of anywhere from inches of water column up to about 6 to 10 pounds. And the big difference between the 2 regulators here is that the 461 is going to always flow less gas than the 441. The 461 is smaller than the 441. The 461 has smaller orifices than the 441. And so therefore the 461 just flows less gas. So they both can handle the same gas pressures for the most part, but the 461 is going to have lower capacities than the 441. So these are low pressure regulators here, the 461S and 441S. Then we go up to our medium pressure regulators here. This is going to be our 57S regulators. So the 461 57S flows less gas than the 441 57S, but they can handle the same amount of pressures. And these medium pressure regulators, these are going to allow outlet pressures anywhere from 3 pounds to 100 pounds. Then finally, we have our high pressure regulators. This is the 441X57 and 461X57. So high pressure here refers to outlet pressures between 75 pounds and 250. Now we have some overlap between like the medium and high pressure regulators when it comes to what these regulators can be set to. And even on the low and medium pressure, there's some overlap on what they can be set to. And that allows in the field, if you have one, to not have to switch out and go to a completely different regulator model if you need to up the pressure a little bit. So the first range is the low pressure is going to be anywhere from up to 6 to 10 pounds. Medium pressure is going to be 3 to 100. And high pressure is going to be 75 to 250. And that's what you can set these regulators to. All right, let's talk about the specs and the different features on our low pressure regulators here. So the 461S is available in a 2-inch body, whereas the 441S is available in a 2, 3, and 4-inch body. The 461s are only available in 2 inches. You cannot get a 461 larger than 2 inches. It's because those are your lower capacity regulators. So if the 461 is not big enough, then we go up to the 441, and then you can go up to 3 and 4 inches. The 461S, both of these regulators can come in screwed bodies or ANSI 125, 250, 300, depending on your MAOPs and your inlet pressures. The inlet pressure on these regulators on a 461, if you look at the bottom of the screen on the bottom left-hand side, you can see that the inlet pressure actually depends on the diaphragm case size. So if you have a 12-inch diaphragm, the inlet pressure is going to be 100 psi. But if you have a 8 or 8.5-inch diaphragm, the inlet pressure is going to be 175 psi as far as the maximum inlet pressure you can have. Outlet pressure on this, 2 inches to 10 pounds, and the 461 flows less gas than the 441. So this 461 is available in an 8, 8.5, or 12-inch diaphragm, and the diaphragm case can be cast iron or aluminum. Our 441S, that's only going to be available, that's going to be available with diaphragms anywhere from 10 to 20 inches in increments of 2. And those body sizes range from 2 to 4 inches. So we have more options there on the 441. Inlet pressures in the 441, because it's a bigger regulator with bigger orifices, the inlet pressure is limited to 100 psi. As you get bigger and bigger orifice sizes, it really limits the inlet pressure you can have into that regulator. Larger orifices typically have lower maximum inlet pressures, and that's why here the 441 is restricted to 100 psi inlet. Outlet pressures on these also are a bit lower, only going up to 6 psi, but this can flow more gas. If you had a situation where you needed to cut down from, let's say, like 200 psi all the way down to 7 inches of water column, you'd want to use 2 cuts. We don't have a regulator that's great for one single regulator that can cut down from 200 psi to 7 inches of water column. That also result in a pretty big temperature drop as well in your gas. So what you want to do there is you'll want to use 2 different regulators. One regulator to cut it down from 200 to, I don't know, let's say maybe like 60 pounds. And then another regulator, either of these would work to cut it down from 60 pounds to 7 inches. So using multiple cuts is a great option when you have a big pressure drop that you need to accomplish. Another thing to note here, so for our 441, for our 461s, they're available in single or double valve assemblies. Here you can see a drawing of each of those. So on the left-hand side, we have our double valve assembly, and on our right-hand side, we have our single valve assembly. So the 461 is available in both single and double. Our 441 regulators are only available with double valves. The double valves give you larger capacity, and there's some other advantages to having double valves as well that we'll talk about on the next slide. But the thing to note here is just 461s, you may see them with single or double valves, whereas the 441s will always have a double valve. The 441s are also just going to have larger valve sizes. So the 441s, the valve sizes start at 1.5 inches and go up from there, whereas with our 461s, valve sizes are either 11/16 or 1 inch, single or double. So our double valve design, these double valence valves are, we think, a huge advantage in using our regulators. In a standard single valve regulator, the high pressure gas from the inlet side pushes down against the seat, trying to force it open. This inlet pressure effect forces the diaphragm to work harder to maintain a steady outlet. With a double valve design, the inlet pressure pushes up on the top valve and down on the bottom valve. These forces cancel each other out. Therefore, the diaphragm doesn't have to fight the inlet pressure. It directly responds to the downstream demand, leading to extreme accuracy during inlet pressure fluctuations. Regulators with double valence valves also have higher capacity than the equivalent regulator if it had a single valve. This allows our regulator to maintain outlet pressure control at higher flow rates. I know we've heard that a lot of technicians and guys that haven't been in the industry for very long aren't used to working on double valves and aren't very experienced on that. And we have some great resources we're going to talk about at the end, to where if you're out in the field and you're trying to figure out how to set a regulator that has double seats, double valves there. We have a YouTube video that walks that through step by step. So we'll highlight that at the end of our presentation. Now moving on to our medium pressure regulators, the 441 and 461s, the 57S regulators. So again, just like our S case regulators, these are gonna, the 461 is only gonna be available in 2-inch, whereas the 441 is available 2, 3, 4, and now a 6-inch as well for this model. You can get these regulators in screwed bodies or ANSI 125 all the way up to 600. Inlet pressures here, it's going to be up to 1,000 pounds on the 461, up to 750 on the 441. And your outlet pressures are going to be the exact same range here, 3 to 100 pounds. And unlike the S cases, with these regulators, they can actually share springs. So the red spring in a 461 57S is the same red spring in a 441 57S. So the springs are interchangeable. They also use the same rollout diaphragm, the 57S rollout diaphragm. So those are one diaphragm size available, and the 441s will have higher capacities than the 461s. Now, looking at the X57 regulators. So these regulators are very similar to the 57S regulators, but we have higher spring ranges available, and we use a smaller diaphragm as well. So again, the 461 is only going to be available in a 2-inch body. The 441 is available here only 2 and 3-inch body sizes. We start at ANSI 250 here because your inlet pressures are going to be pretty high looking at those outlet pressure ranges. Inlet pressure is up to 100 pounds on the 461, 750 on the 441. And outlet pressure ranges 75 to 250. Again, with these regulators, the springs are also interchangeable. So a red spring on the 461 can be put in a red spring on the 441 here. They use the same rollout diaphragm, and the 441s have a higher capacity than the 461s. So both of these regulators, the 57S and X57 models, they use the rollout diaphragm. This diaphragm doesn't stretch, it rolls out instead. And by rolling out, the area is controlled and decreases as the regulator opens up, while the area of a normal, standard, conventional diaphragm would increase as the regulator opens up. When outlet pressure drops and the regulator opens, the pressure on the diaphragm acts on a smaller area, which results in less of a force countering the spring. And then as the outlet pressure would increase and the regulator closes, the diaphragm area increases, increasing the force pushing up on the diaphragm, helping to close the valve. So these help eliminate that diaphragm effect and decrease droop. And here you can see the performance of these regulators. These regulators perform with outlet pressure, keeping that outlet pressure very close to the set point, up to very large flow rates, almost eliminating droop compared to pilot operated regulators. However, while pilot operated regulators provide good outlet pressure performance, they do react slower than these regulators. Our regulators react faster. And so using a rollout diaphragm, we're getting performance close to a pilot operated regulator, but with faster response. So when you compare these regulators, the 57S and X57 regulators to pilot operated regulators, our regulators react faster than the pilot operated regulators, and that's because the pilot's not sensing and responding directly to changes in downstream pressure. They have an intermediate load. Pilot operated regulators also require higher lockup pressures during no flow conditions. They need additional pressure to lock up both the pilot and the main regulator diaphragm. And lockup pressure in a pilot operated regulator is also determined by the monitor regulator. Next, the third bullet point there, freedom from freeze up. Pilot operated regulators use smaller orifices and are more susceptible to freezing. I know I was talking to a customer in Canada, and they love these regulators. They call them the icebreakers. These are installed all throughout Canada because they operate great in very, very cold conditions. Just with the larger orifices, with the way the body's assembled, it's going to break up any ice in that gas, and perform well when you need it to at most when it's coldest out. Finally, there's less moving parts in our regulator than in a pilot operated regulator. And so they're more reliable, less moving parts, less points of failure, and easy to maintain. So looking at maximum inlet pressures on these regulators, just wanted to put this slide up. You can see here, if you're using a threaded regulator, the maximum inlet pressure really there is going to be 250 psi. And then for different ANSI ratings, you have different maximum working body pressures. And you want to make sure your inlet pressure never exceeds these pressures here on this table for the option that you select. But in addition to this table, there's a couple other things that can determine maximum inlet pressure as well. So that body rating that we just showed, and then the valve or diaphragm selection, depending on the regulator model, that can also determine your maximum inlet pressure. And then finally, seat material. So we'll talk about seat material in the next slide. But right now I want to focus on a valve or diaphragm selection. So when I look here, on the left-hand side of my screen here for the 461, for the 461S, that inlet pressure is going to depend on that diaphragm case size. If I'm using a 12-inch diaphragm, it's 100 pounds. And if I'm using an 8 or 8.5-inch diaphragm, it's 175 pounds. For the 461-57S and 461X57, because those use smaller diaphragms and small orifices, our maximum inlet pressure there is just 1,000. You're never going to be exceeding that. On the 441, for the 441S, maximum inlet pressure is 100. And then for the 57S and X57, these regulators, it depends on the orifice size. Because we can use orifices that are so large, anywhere from 1.5 inches all the way up to 4.25-inch orifices, it really restricts that maximum inlet pressure. And so here you can see on these tables, that maximum inlet pressure is going to decrease as you utilize larger and larger orifice sizes. And that's the same thing throughout all of our regulator models. Sometimes it doesn't come into effect, like on the 461 57Ss, you're using orifices that are pretty small, whether it's 11/16 or 1 inch. So it doesn't really come into play there, but on our 441s, it definitely comes into play here. And so you want to make sure that you're not exceeding these maximum inlet pressures. Another thing to keep in mind when selecting a regulator and when you're out in the field, looking at what pressures you have and what regulator you have, is going to be seat material. So we have a variety of different seats available for these regulators. You can see the 5 seats shown there. And the seat material you choose impacts 3 things. It impacts the maximum pressure differential you can have through the regulator. It impacts the maximum inlet pressure, and it impacts lockup. So lockup, again, refers to the ability for that regulator to close when there's no flow or that gas is shut off. And the regulator is going to close at a pressure that's slightly higher than your downstream set point, and that pressure is your lockup pressure. The harder seat material you have, as we go on my the 5 seats here from left to right, the harder seat material, the higher lockup pressure you're going to have. So polytan is going to have a higher lockup pressure than polyred, and polyred is going to have a higher lockup pressure than Buna. So we ideally want to use Buna seats because they have the lowest lockup pressure. However, with softer seats, you're limited on maximum pressure differential and maximum inlet pressures. So you can see the harder the seat you use, the more inlet pressure and the more pressure differential you can have in these regulators. It's really an optimization. You want to make sure you're selecting the right seat for your application. And you can see here the 5 options we have. Buna we see the most of. Polyred and polytan are also very popular, especially in regulator stations and gate stations. Viton specific, it's more resistant to chemicals. It's slightly harder, and it has a max differential of 250 psi, and it can actually go up to 300 degrees Fahrenheit, where these rest of the seats are limited to 150 degrees Fahrenheit. And then nylons are hardest seat material, and that's used if other seats are really being damaged at high flow, high pressure sites like gate stations. I haven't seen too many nylons. I haven't worked too much with those. Typically we see Buna, Polyred, Polytan going through for gas utilities. V-port. So some of you may be familiar with our V-port retainer, and some of you may not. The V-port guide is a wing retainer that sits on our valve stem there and holds the seat in place. So here you can see it right here. And this V-port allows the regulator to maintain outlet pressure performance at lower flow rates, essentially increasing the turn down. Now, when sizing regulators, you want to use a standard turn down of 20-1 and a turn down with the V-port of 40-1. But our regulators have really been installed throughout the country at much lower flows than that in situations, and they perform great through, winter maximums and summer minimums. And so we believe that our turn down is probably higher than what we size them at. But a general rule of thumb when sizing regulators is to use 20-1 for a standard retainer and 40-1 for a V-port. Another thing the V-port can do, in addition to allowing that regulator to operate better at lower flow rates, it also helps the regulator maintain outlet pressure. If you're experiencing any outlet pressure pulsation when the regulator is operating pretty close to the set point, it helps the regulator have a smoother opening and closing of the valve versus constantly slamming opening and closing by increasing that surface area that the gas is going through the orifice there. Also, make sure that you're using the right reduction in our capacity tables if you're using a V-port. You see it here in the bottom right. There is a reduction that you'll need to use. So for example, this first column here, if you're working on that column, you'll want to make sure you're multiplying the capacity table by 0.65 if using a V-port. Then the second column there is 0.94 and so forth. So there is a slight capacity reduction with these. That reduction can vary. You want to look at our literature, and those are posted in there. Another thing to note, the spring determines the outlet pressure range. So when I, mentioned that the 57S regulators had a range of 3 to 100 PSI, we have different color springs that we can put in that regulator, and that spring is going to determine what outlet pressure range you have available. So here you can see a yellow spring has an outlet pressure range of 3 to 6 pounds, a gray spring has 5 to 9 pounds, and so forth. If you're in between two springs, this is a good example here. If you have 5 PSI into that regulator, 5 PSI you want out of the regulator as your set point, here I would use a yellow spring. Ideally, I want my pressure that I'm setting the regulator to be on the upper end of that spring range. Springs operate better when they're more compressed than extended, and so choosing a spring range where I'm towards the higher end is ideal. Although sometimes you'll just have to pick the one that yours falls in between.
I have a quick question for you, Jake.
Yes.
Do our rebuild kits come with valve seats, or do we need to know what the valve material is? Does that need to be specified when ordered?
Yeah, so rebuild kits, so we have a standard like repair kit that we have started selling with our regulators. I actually have a slide on that. I'm going to get to it, but those repair kits contain all the soft parts for our regulators, things like O-rings, diaphragms, tetraseals. They do not contain the seats. If you need new seats, you'll need to order either the seat itself or a valve assembly, and we'll always make sure we ask what type of seat material you need when you're ordering a seat or a valve assembly. We see that ordered pretty common where a customer will call in and they will request, maybe they're changing orifice sizes. So they have a 441 57S and they're going from 1.5 inches to 1 3/4 inches. Well, in that case, we'll make sure that we know what seat material you have, and we'll get you a new upper orifice, a new bottom orifice, and a new valve assembly with your 1 3/4 inch seats. Maybe you just have a seat that's gotten beat up in the field. We'll request what material you have, and we'll get a replacement seat for you or a replacement valve stem. We can do it either way.
Great, thank you.
All right. So overpressure protection here. There are four main types of overpressure protection that we see in our industry. And with these regulators, we typically see them used with monitor regulators. So it's actually a third square there. These regulators are too large to have internal relief valves. You can use external relief valves on these regulators, but we really feel like for the first form of overpressure protection, monitoring is the way to go. You can also have external slam shuts, but then you do that, you're potentially shutting off the gas downstream. So when we look at monitor regulators here, a monitor set consists of two regulators in a series, one of which is a standby. So here on my picture, the left-hand regulator here, my upstream regulator is my monitor regulator. You'll notice that when you're using a monitor regulator, both control lines are piped downstream of the second regulator. So both regulators are sensing the pressure downstream of the regulator pair. And that monitor regulator should be set slightly higher than the operating regulator. So maybe the monitor is set at 50 pounds and the operating regulator is set at 47 pounds. So if anything happens where that operating regulator fails, the monitor regulator would take over and regulate that gas to the slightly higher pressure of 50 pounds if the downstream pressure started to increase beyond, got up to 50 or beyond. So it's a good way to have overpressure protection. This is the most common thing. Usually when we sell these regulators, we're selling them in pairs. One is a worker, one is a monitor regulator. Usually you can use the same regulator for the worker and monitor. You just will need a different spring in there for a different spring range. You want to make sure that the set points aren't too close together. General rule of thumb is about 10% apart. One common one I see a utility use is 7 ounces and 10 ounces. Another one is like 42 and 45 PSI. We've seen utilities choose different numbers, but generally about 10% apart. You want to make sure the regulators aren't too close together. There's some piping in between the two. Although I have seen them piped up right next to each other and it was working, but generally rule of thumb is you want to have some pipe in between the two. And then just note that when you're using a monitor regulator, this decreases the capacity of the regulator by 30%. So if we had one single regulator here and that regulator had a capacity of 1,000 cubic feet per hour, if I introduce a monitor regulator, that's going to decrease my capacity to 700 cubic feet per hour. So just keep that in mind, that monitors do decrease that pressure or that capacity. You saw in that previous slide, we had these two control lines here. I'll actually back it up. You can see these two control lines piped downstream in my drawing. It's very important that these control lines are installed properly. A lot of the troubleshooting calls we get are around improper control line placement. And so we really want to make sure that the control line is sensing a smooth flow of gas, and it's the same gas that the burner or boiler or whatever you're using downstream is going to be seeing. And so we want this away from any flow disturbances, things like elbows, T's, or other flow disturbances. We want to make sure it's not right up at the outlet of our regulator, about 8 to 10 pipe diameters away from our regulator. Another rule of thumb I like to use is about at least 4 pipe diameters away from our last flow disturbance. So if you're 10 pipe diameters away from the regulator, but you're right up next to a T or right after a control valve, that's not going to be very ideal. We want to make sure that it's on flat piping away from elbows and T's and getting that laminar flow. Also, some other rules here. You want to make sure that it's on top of the pipe. That way, if no debris can clog it. You want to pitch it to drain away from the regulator. You want to make sure that you're using a control line size greater than or equal to the size of that control line tap. And if you're planning ahead, our control line tap sizes are in our literature. You want to make sure for every 20 feet of control lines you have, you use go up one nominal pipe size. And then overall, most important thing here is just to remember that the regulator is controlling based on the gas that it's being sensed through that control line. And so you don't want those turbulent flow conditions. So here's an example of good control line placement. You can see here, we're using two control lines for worker and monitor regulator. They're both placed downstream of the second regulator. They're on flat, smooth piping here. Another thing to note, I forgot to mention on the previous slide, but very important, do not share control lines. If your worker and monitor is sharing control lines, they'll really they'll kind of start fighting each other, and that's something that we've seen be a problem. So make sure that each regulator has its own dedicated control line. Another reason for that is if something were to happen to that control line, well, if something happens to your control line and your worker and monitor regulator is sharing a control line, you just lost your overpressure protection. You just lost both regulators. If that control line were to break and be exposed to the atmosphere, the regulator would think that there's no downstream pressure. We need to go wide open to feed gas downstream. Well, if that were to happen on both your regulators, now both regulators are wide open, just allowing gas to go through downstream, and you have no regulation, no overpressure protection. So we really want to make sure that we're using individual control lines and that they're piped properly. So this is a good example of that right here. Here's an example of control line placement I don't love. Now these are 122, 121 regulators. And this customer, when this customer was calling in for troubleshoot, they had an issue running off of the two regulators, the 121s here up top. When they ran it off the bypass on the 243 on the bottom, it was working just fine. That really didn't surprise me because there's a couple of things about this installation I don't love. First off is just the amount of elbows they introduced into the system. I mean, we have 1, 2, 3 elbows going in the first regulator, then another 3 elbows elbow directly into the second regulator. I don't love that. We don't have necessarily set upstream or downstream straight piping requirements, but you want to have some. So I didn't love that going into the second regulator. And then, of course, this control line placement, this is going all the way up and over. This one's all bent. And then they're piped into a control line right before it increased sizes to a larger pipe size. I would have rather had the control lines placed on this larger pipe size, getting a good sense for a good laminar flow and getting a sense for that true downstream pressure that the building's going to be seeing here. So we have some issues with that control line piping here. Here's one that's maybe not ideal, but pretty good for the situation. I mean, at the end of the day, I'd probably like to rather see it on this flat piping, but overall they're on the side of the pipe, so I'm not too worried about debris getting in there. And that is on smooth, straight piping there, not piped directly in an elbow. These elbows are also a little smoother out on the flow than a straight 90 is. And so this was an example of okay control line piping. So here's some examples of regulators out in the field I wanted to share to show you guys what we have found. So this regulator was installed in 1968, and then we talked to this company in 2024, this utility, and these regulators have been working without a problem since 1968. We also know that they haven't been opened up. There's like a period of time from I think it was like 1985 to 2020, 2021, where these regulators were not really maintained or serviced. They don't think properly with the previous ownership of that utility. And so really this is just an example of our regulators working from 1968 up until this was taken in 2024 without any issues, even if they weren't really serviced that often. And I can just imagine the load profile on these regulators have changed over time. The pressures have changed. Yeah, these regulators have worked out well. Here's another example, and you can see here every time they go out, every year when they go out and do their regulator station inspections, they're pulling great data. They're taking a look at the pressures. The regulators are operating as expected, as they should be. Through the summer minimums, winter maximums, these regulators feeding an area that's seen a lot of growth. So I'd imagine the load for these regulators have doubled or tripled over the years, and yet regulators are still operating fine. Here's another example of a regulator, and this regulator is feeding a little industrial park, and yet we see them operating well throughout all the years. Every time they go to it, we're right within the range that we should be for our set points. So looking at improvements that we've made on our regulators. So one thing that we've done is we've come out with stainless steel valve stems, stainless steel orifices. These are things that Sensus has done to improve the regulators. So switching from brass or plated steel to stainless steel for a number of different components. They designed the V-port for better turn down and better outlet pressure control, and also redesigned a stem bushing for an anti-friction stem bushing. And we're looking at improvements to make as well. We're constantly getting customer feedback on things we can do to improve these regulators, and we're currently, thinking about that right now. I know there's a question earlier about parts kits. This is our standard repair parts kit. It's going to have your vent, your diaphragm, O-rings, and Tetra Seal there. If you need valves, so our valve stems, seats, orifices, we typically sell those as well. All those part numbers are in our manuals, but if you tell us, hey, I got a 46157S, I'm changing it from 11/16 single regulator to 1-inch double valves, we can get you the parts you need to make that conversion. So overall, these regulators provide a simpler maintenance and a lower maintenance cost than pilot operated regulators. You don't have to do maintenance on them as often, and there's less moving parts. We have that near pilot operated performance on our 57S NX57 models, but they respond faster and are simpler. These regulators utilize larger orifices, reducing the risk of freezing. It's common for these regulators to stay in service for decades. I've talked to utility a couple months ago, and they have a couple of Chaplin-Fulton regulators they're going to be replacing. So that tells me those regulators were installed pre-1963, which is pretty incredible. And we see that often. We see Rockwells out in the field all the time, and some Chaplin-Fultons still out in the field as well. Finally, we have a variety of different models and valve sizes, so we can provide a wide variety of capacities. So looking at here for resources, we have instructional hands-on YouTube videos on our YouTube page, and then you can find all of our documentation, our rebranded brochures and manuals on our website. We did just issue the first round of revisions for our brochures and manuals. So we found some errors that were made when we rebranded them, and we got those all fixed. So the latest documentation can be found on our website. And I want to talk a bit about these YouTube videos. So we have a number of different videos on how to tear down and rebuild 441 and 461 regulators. We have videos on how to rebuild valve assemblies if you're changing out the seats. We have videos on how to assemble the diaphragm as well if you're just replacing that rubber diaphragm but want to keep the same diaphragm stem and valve stem there. So we have videos on how to do all the work on our regulators. They're great to use, especially if you're out in the field, you're not sure what to do. Instead of reading a manual, you can just pull up the video. I know I do that all the time, working on my house, YouTubing random things, how to do this, how to do that. Our YouTube videos operate the same way. The two videos I really want to highlight are how to set double valves. So this is something we've heard a lot from utilities. There's a lot of new people in this industry that haven't worked with double valves before. And we have a YouTube video here that takes you through step by step on how to do that. Close-up video. This is Jack here. He talks through it step by step on how to do it. So double valves don't need to be a very daunting or unknown task. These YouTube videos will walk you through step by step. I encourage you guys to share them with everyone in your organization. They're really great resources to have on the field. Everyone's got a smartphone, everyone's got YouTube. You can pull them up, especially for technicians that haven't done this work in maybe 6 months, 8 months. They haven't seen any of these regulators. And then they go up to one, bam, here you go. Here's how you do it. Finally, when we talk about sizing a regulator here, some rules to keep in mind. We want to size for about 20% more than you need to account for a droop, and that's the reduction in outlet pressure as the flow increases. There's that 30% reduction when using a monitor. Even though the monitor will be wide open, it still adds that flow restriction. There is a capacity reduction when using a V-port, and double that last bullet point there, I include this on all my sizing slides, but you're probably not going to experience that with these regulators. We're talking about enough flow that I don't think the fourth bullet point really comes into play that often. You'll see us doubling the capacity required when using a generator high efficiency boiler with our 243 regulators or our 121, 122 regulators. That's something we might not be as worried about with these, because since these regulators are faster responding with larger orifices. General rule of thumb here, you want to use the regulator that has the smallest orifice that will handle the flow. So larger orifices have larger capacities, but we want to make sure that as long as we're for 20% more than we need, and we have our reductions, if we're using a V port or we're using a monitor, you want to pick the smallest orifice that works for all of those things. So I've come up with a spreadsheet here. It's our sizing tool. And this sizing tool is very straightforward. On the left-hand side in site information, you'd put in your inlet pressure, your outlet pressure, your max and min flow rates. If you don't have a min flow rate, just make them the same. Whether you're using a monitor or not, most likely you are. And then the tool spits out two things. First, on the bottom left-hand side, it spits out a regulator selection. So here for these numbers, you can use a 44157S regulator with a 2-inch body, 1 3/4 orifices, and Buna seats. It also tells you the max capacity of that specific regulator selection at your pressures. On the right-hand side, it gives you a table that shows you all of our different regulator models with the different body sizes and orifice sizes available. And it shows whether those regulators will work for your specific application. So maybe you have a 1.5-inch valves, not 1 3/4 valves out in the field, and you want to see if that can still work. Well, if I go to my table here and I go to 1.5 inch, you can see this yes, no column will tell you whether it can work or not. So here that regulator will not work for my application. I'll need to go to 1 3/4 valves. I'll have Katie send out this sizing tool along with an instruction guide on how to use it. And this sizing tool also uses both standard valves here, that's columns G through J, as well as the V-port columns K through N. So these are the same sizing tables, but if you're using a V-port, it reduces the capacity a little bit and reduces your minimum, which is a good thing. There's also another tab on the sizing tool that just has all your spring ranges. So that's the final component of selecting a regulator. You can just go over one tab and see what spring you need. So it's a pretty neat sizing tool, useful to use. We'll make sure we get that sent out. I'm going to pull back up our resources page here and then stop. We have 6 minutes left. If anyone has any questions, I'm going to see if I can pull up the questions here, and yeah, we can answer any questions anyone has.
Yeah, if there's any questions, you can put them in the chat function or the Q&A. But if not, like Jake said, we can get these materials sent out. I'll get a recording of this uploaded to also our YouTube page. So you can go to our YouTube page at any time to view this webinar or the sizing webinar that Jake put on previously. That might not be till Monday, but might try to get it out today if I can.
Do we have classes on properly selecting, setting the regulators? So I think our YouTube videos are a great place to start because those can be accessed anywhere by anyone. Now we are giving a class at the Western Gas Measurement Short Course coming up in May. We're also giving a class, a 3-hour-long class at the Appalachian Gas Measurement Short Course in August. In addition to that, you can talk to your sales reps and see if a class makes sense for you. But the Western Gas Short Course and the Appalachian Short Course will be giving a hands-on breakdown on setting the valves and fully tearing down and rebuilding one of these regulators. But really, you know, I've given that class a number of times now, and everything I needed to learn for that class, I've learned from going to our YouTube page and watching those videos and then just practicing on my own. And so I really think those YouTube videos are just a huge resource that will really help you guys out when you're out in the field.